I hope you guys can see me. Hi, I am Shrikar Babu. I am from the electrical department from IIT Madras. I'm one of the team leads of the AI club. I couldn't attend the first session. I'm here for the second session and I'll be teaching a little bit too. AI club from IIT Madras, we are a part of Center for Innovation in the IIT Madras in IIT Madras itself. We as a group of students, we try to spread awareness about artificial intelligence and we teach how to learn, how to actually what is there in artificial intelligence and many more like that. This is what we do. Okay, before we start off with this session, I have a couple of announcements. First things first, the session is completely free. I've heard some of you are getting some spam messages asking for money. They are not from us. They are not reliable and they are not um, accountable for anything. Remember that these sessions are completely free of cost and you are not going to pay any money. Um, Apart from that, all the resources, everything you need for the session, for the summer school will be there on the GitHub page. I will show how the GitHub page looks and how to utilize, how to get the most out of GitHub. I hope you can see my screen. Okay. This is the GitHub repository. When you click on the link we have shared, this is the screen you'll be seeing. So what is there exactly? If you click under session 1, you will see a bunch of files. I hope you can see a bunch of files. And under that, you will see a README file. In the README file, you can access all the presentations, including notebooks and the presentations which our coordinators have presented over there. Along with that, there'll be also a link for session recording. This session is uploaded on GitHub, on YouTube, sorry, on YouTube, and you can access it there. This meeting is also being presented, is also live streamed on YouTube. You can check that out as well. This is for session 1. You can see there are all the notebooks used and the presentation used, and also the session recording. Apart from this, there is also something called as there's also some resources to understand how to use Git properly. And these three are some YouTube videos which will help you getting started with Git. If you see properly, I think you can see the session 2 resources as well. You can see the PDFs presentations, which are PDFs, and the notebooks which are being used for this session. We will present through all of these notebooks soon. I hope you get used to GitHub properly, and this is the README on the repository file. You can find the task 1 here, and you can find all the necessary recordings and sessions. Okay. Another announcement coming to task 1. A lot of you have asked what to do exactly in task 1. I will let you know what to do exactly in task 1 in today's session. Task 1 is supposed to be on pandas, numpy, and matplotlib. You haven't learned matplotlib yet because we didn't teach that particular library till now. It will be taught in another 5 minutes. After that, you will be able to attempt this task 1. From task 1, what we expect is very, very minimal. Whatever dataset you have, you can do whatever you want with the dataset. We have given, there are multiple columns, there are multiple rows of data where you will try to plot them or you will try to describe them using pandas, or you will try to take, for example, let's say I want to take the mean of monthly income. I want to analyze what is the mean and what is the median, or even what is the mode of the monthly income. You just try to use NumPy and interface it with this data set to get the mean, mode, and median. You can just report this under a markdown or in your code, whichever whichever notebook you're trying to submit. Mention that this is what I found out. It is completely exploratory. We don't expect anything concrete from this task 1. You just have to explore the data set and see what is an observation that you can make out of this. And we will just go through those submissions. There's nothing concrete again we want specifically from this task one. I hope that is clear. This is regarding GitHub. This is all we have right now. Coming to first session was about intro to Python, NumPys, and Pandas. You have just been introduced to Python, where all the important functions, all the important syntax has been introduced to you. From second session onwards, we will be teaching how to use this Python language to actually understand what machine learning is. Till now, you have not been introduced to what machine learning is. This session, we'll be introducing what machine learning is, and we will try to explain how the code works. Even if you didn't understand how Pandas exactly works or how NumPy exactly works, from session 2 onwards, you will see how the syntax is being used for machine learning purposes, and you can easily grasp how to use all of the commands. This is all with the announcements. If you have any doubts till now, you can raise your hands quickly, or else I'll move on. Any doubts? Okay. If you have any doubt, unmute your mic and please talk, or you can even chat on the YouTube live stream. Our moderators will help you with that. Okay. Now let's start with the session. Firstly, let's start with Matplotlib. What is Matplotlib? Multiple times when you're working with machine learning data, you would want to see how it looks. Looks is a very big I'm using here. Looks is basically a visual representation of the data. When you say, when you have a certain column of data which is corresponding to another column of data, you would want to see how visually how that relates. And that is the main reason why Matplotlib has come into picture. You want to visualize your data. Matplotlib acts as a tool that will help you visualize your data. Let's see the imports first. For any library, there are certain imports, and the import starts with, from Matplotlib, import pyplot. Pyplot is another sublibrary inside Matplotlib, where under pyplot there are multiple functions, or pyplot itself is a function, you can say. Pyplot will help you visualize the data. And coming to the second line, matplotlib.image will help you visualize an image which you already have. I will show you how to use that as well. If you say import matplotlib, it will import the entire library. Import numpy as np, I hope you got that from the first session. Import pandas as pd, I hope you got that as well from the first session. That is all from the imports part. Now let's see the most basic function which is being used in in matplotlib. It's called plt.plot. If you have a list, if you have two lists, each corresponding to one another, let's say there is 1, 2, 3, list 1, and 4, 5, 6, another list. You can plot these data. You can plot the points 1, 4, 2, 5, 3, 6 in such a manner. You say plt.plot and remove all of these commands. Let's remove all of these commands for now. And you run this cell. Let's see what happens. Okay, I didn't run the import cell. All the libraries are imported now. And see, this is how the graph looks. It is simply, it plots the points 1, 4, 1, 2, 5, and 3, 6. Now, what were the previous attributes which I have just removed? What they do are, label gives a label to the graph. It won't be shown in this particular cell, but remember that label gives a label to the graph. I'll show you how that is used. Color will color the graph, will color the line which is being drawn. And line width, I think it's pretty obvious. It will define the line width. MFC is basically the marker, the point which you want to mark will be given a certain particular color, and that color is, what is marker equals 8? I will explain what the different types of markers are in some while. Let me scroll down a little bit and you'll get to know what those markers are. If I say marker size is equal to 15, it will fix the size of the marker as 15. When I say marker edge color is yellow, it will color the edge of the marker as yellow. And the line style, there are multiple different line style. You will have to look up these on Google, no one remembers these in mind usually. So you have to look up for what the different type of line styles are. If you say this is how the line graph looks. I hope till now everything is clear. These are all just attributes of the plt.plot function. If you have two different lists, if you want to plot them, this is how you plot them, and there are different attributes, and this is how it will look. Okay, coming to markers. What are markers? Markers are these points you see here. These points you can make it in different shapes. For example, I use the marker size 8. 8 corresponds to an octagon marker. There are multiple different markers. For example, let me use V here. Let's see what happens. We get a triangular marker, as V corresponds to triangular marker. That's all. This is the most simplest command you can find. Next, coming to, if you would want to short all of these commands into a one-liner, writing the attribute every time might be tiresome because you will be dealing with a lot of this when you're doing machine learning.
Can you zoom in a little?
Sure. I hope this is fine. Okay, moving on.
Yeah.
See, when you're dealing with machine learning specifically, you would want to plot a lot of these functions. To make it faster, there is a concatenated version of the command. If you say this, if you can see what I'm trying to say, if you say this, it will plot exactly what is trying to what exactly is we are trying to say. R dot is a combination of the coloring attribute and the line style attribute, which is basically the line style attribute and the color attribute. Concatenated together, you can just say R dot dash dash. And label when you say 2x, without saying plot dot legend. Let's say if I remove plot dot legend, this particular label won't show up. See, if I say plot dot legend, then that particular legend, that particular label will show up. That is how we use that particular part. I hope this is also clear. Then let's move on to some other basic commands.
Srikar, can you zoom in a little more?
Sure.
Yeah, this works.
Okay. There are some other commands such as plt.xlabel, plt.ylabel. They give labels to x-axis and y-axis. Plt.title gives the title to the graph. X-ticks and Y-ticks. What are X-ticks and Y-ticks? You usually don't use them in machine learning often, but it's good to know. X-ticks and Y-ticks are basically what points on the X graph and what points on the Y graph do you want to exactly point to. For example, if I say 0, 1, 2, 3, 4, 5 and 0, 2, 4, 6, 8, 10, it basically marks 0, 1, 2, 3, 4, 5, 0, 2, 4, 6, 8 on respective X and Y axis. This is the usage of X ticks and Y ticks. And if you see, there are two lists, X and Y. Again, similar concatenated version of writing this. Marker size is set to 10, pretty much everything is the same. Okay, if you want to set the title to a particular font, you do this in this particular manner. But as Google Colab won't support other fonts except its original font it uses, if I try to say Verdana Roboto, it won't do it because the Colab won't do it. But if you're using a local PC, then that should be, if you're using a local environment, that should not be a problem. Now, often in machine learning, you would want to plot two or more graphs on the same plot to see how each of them compare with each other. That is done through matplotlib itself, but this time you just say plt.plot 2 different times, but you call plt.show only once, so that it draws the same graph on the same figure. It draws not same graph, it draws 2 different graphs on the same figure. Let's say if I have 2 different sets of lists, 2 different pairs of points I want to plot. One is 2x, y is equal to 2x graph, and the other one is y is equal to x square graph. This is done in the same similar manner like before. You call plt.plot once and you call plt.plot again. And usually to differentiate between these two graphs, you set the color of both of them different, and you try to change the line style, or you try to change the marker size, or even sometimes you even change the marker's edge color, so that if there's a point coinciding with each other, then you can see that there are 2 points there. For example, like this. I hope this part is clear. For example, let's say I remove this so that line styles are different. Yes, if I do this, the line styles are different, so we can differentiate between 2x and x squared graph. Okay. Now coming to bar graphs, this is all about plotting line graphs. Line graphs are the most frequently used ones, and bar graphs are also equally frequently used. Bar graphs are basically, you know what bar graphs are. If you have A, B, C, and if you have the not cumulative frequency of each of the occurring, you would want to see how the bar graph looks, how each of them correspond to how many times it occurs. And this is how the bar graph essentially looks. It's plt.bar with x-axis as each of the titles and y is the frequency. There is another function called bar h, which will plot these bar graphs horizontally instead of vertically. But usually we use vertically. Horizontally is very rarely used. Okay. If you want to make your bar graphs looks very fancy, you can use different functionalities of set hatch that will essentially make your bar graph look cooler. That is all to it. There is nothing much to this. You can see the syntax for a little while. plt.figure will let you resize your figure. Basically, this figure size, it will let you change how many pixels you want. If you're using a local PC, it is more evidently seen because a new screen will pop up, and that pop-up screen will change its sizes. But overall, all in all, that is what the functionality of plt.figure is. Finally, I just mentioned before the session like at the start of the notebook, I mentioned that there's something called plt.imshow or plt.image. Let me scroll up to that. The import for this is matplotlib.image as in img. This will help you look up images basically. As of now, I don't have an image which is in my contents folder. Let me upload a test picture. Now you can see your test picture has been uploaded. You would want to view this image in your notebook, and the best way to do this is using matplotlib. Matplotlib has a function called image.imread, which will read the image and store it in a variable called image. And if you say plt.imshow, it will show this variable if it's an image, which is basically that get rickroll. Now, these are all the basic functionalities of matplotlib. If you have any questions, you can ask about matplotlib. I will change to the screen. I'll change to the meeting. Yes. I see there are no more doubts. I see no hand raises. I hope matplotlib is perfectly clear to everyone. Using matplotlib, you'll be able to perform most of the task one. You should be able to analyze some of the data and get to some of the conclusions. We don't. You can just say whatever you want, and you try to look up what exactly you have come up with. That is all from matplotlib. I hope all of you are clear. From now onwards, we'll be starting the crux of machine learning, which will be linear, polynomial, and logistic regression. This is the start of machine learning. All the best for everything. And one more thing, if you find any syntax to be very difficult, if you find any of this to be very difficult to remember or anything, just know that none of us know for these commands by heart. Every time you try to code something, you look it up on Google. Reading documentation is one habit you have to get used to. Reading documentation of each of the functions, how they are used, what are its attributes, are something which you have to get used to. It is not something you will be remembering by heart. Just know that. Even if you don't, like, for example, pandas is a little difficult for beginners. And I think some of you have problems with pandas specifically, you just have to look it up on Google, see how each function is used, see what type of function is used for what, and something like that. Everyone, including me and everyone who's trying to take the session, always does the same thing. They try to look up functions as and when they use. That is all from my side and matplotlib. Let us move on to linear and polynomial regression. Over to Shailesh. He will be taking those.
I hope I'm audible. My voice is clear, right?
Yes, you're audible. You can start.
Okay. Hello, everyone. Good evening. I am Shailesh. I'm currently in my second year from mechanical department and one of the coordinators of AI Club at IIT Madras. So today I will be taking applications of ML, some basic divisions of ML, and most importantly, linear and polynomial regression. So we'll start off. I'll share my screen. I hope my screen is pretty clear. So before we go to all regressions and types of machine learning, we just start off with the most basic question: what is machine learning? So what differentiate machine learning from other types of coding is when you code something, you give very specific instructions to the computer or an algorithm to do a certain program. But what machine learning does is we provide it with a huge amount of data and we just give it some certain tools to know to help it look out something from the data. And the algorithm will look out for some patterns or relationships, or will try to predict something when you give it a new set of data. You can think of it as a pet. When you start training your pet, it won't remember any hand gestures, or it will not give you any pause, or it will not jump when you command it to be. But when you train it for like a year or so, it will start remembering your hand gestures, your voice also. It will start responding to certain commands which you give it. So that's machine learning in a crux. So moving on, today we'll cover applications of ML, which I'll briefly skim through. Types of ML: supervised, unsupervised reinforcement learning, linear regression, and polynomial regression. These two topics will be of the main importance today. So coming to applications of ML, machine learning is one of the most evolving and the most researched field in the world right now, and its uses is widely increasing day by day, venturing into newer and newer fields. Like agriculture, you have processing, image processing in medical. The most the most useful for the current generation would be ChatGPT, which is basically a text generator. So what's a text generator? What you do is you provide it with a lot of text. In case of ChatGPT, it has been provided text from the internet till the year 2021. So based on all the text, when you give it a prompt, it will analyze all those texts, generate the answer based on a prompt, and will provide you the best suited answer. It can be some code, it can be some Python, it can be anything which you want. And then you have virtual personal assistants. In the case of, we have Google Assistant, you have Siri, you have Alexa, which is used in Amazon home devices. Then coming to some serious topics, you have diagnosis using image detection. This is mainly used in detecting cancerous cells. So you will use some techniques like CNN, where the cancerous cells will be captured, and based on machine learning, it will be decided whether it is like tumorous or non-tumorous. That is, it is like very dangerous or it's non-dangerous for now. Then you have autonomous vehicles, which again uses image detection to check for cars on the roads or traffic signals. Best way would be LiDAR and cameras that are being used in Tesla models. Then you have speech to text. You have stock market trading, basically where mathematical models are employed in stock markets to determine which is the best stock to invest on. Then you have spam detection in mails. Gmail usually does that for you. It transfers all the spam mails which you get from various scams into a scam folder. And sometimes it also starts the mails which is like priority for you. And there are a lot more. I can't cover it. It will take an entire session for that. So basically, these are the day-to-day applications of ML. We'll move on to types of ML. On classifying on how the data is being used and the actions that are performed on them, we can divide it into three broad types, which are supervised learning, unsupervised learning, and reinforcement learning. We'll move to supervised learning. So what supervised learning basically does is you provide the algorithm with a set of questions and you provide the same algorithm with the corresponding answers. You provide a huge amount of data to it. And when you give it a new question, it will analyze all the given questions and answers and print an output based on all the given data set. So put in some layman example. Say you have two bunch of fruits, apple and banana. You provide these images to a machine and label all those images as apple and banana correctly. So it will look into features that differentiate these images between apple and banana. Say the apple will be round, it will be red in color, it has a slight depression on top. It might have a leaf on top, I don't know, depends on the images. And then you have banana which is like long, which is yellow in color, pale in color, might be in bunch at once. So these are the characteristics that the machine will try to analyze from the images that you provide and classify them into apples or bananas. And after training the model on this, you will provide it a new image with an apple or a banana without labeling it. That is, without telling it exactly is it an apple or banana. So then the algorithm will look into the exact same features that it used to classify those fruits from the dataset. That it will look whether it's thick, whether it's round, or whether it's long. If it is round and red in color, it will classify it as an apple. And whether it's yellow and long, then it will classify it as a banana. So this is supervised learning on a very basic terms. Coming to unsupervised learning. So if we carry on from the previous example, if you just provide the machine without labeling those images as apples and bananas, it will just try to segregate both images into different groups. That is, it will segregate one group of images which are like red in color and one set of images which are yellow in color. So we don't explicitly label it apple and banana, just give it a bunch of stuff and tell the algorithm to learn patterns on its own. So that's unsupervised learning for you. Another good example might be Google News. So Google News is not a journalism house that goes and reports stuff. What it basically does is it will just gather all the major headlines related to one specific event for you and present to you in a nice and compact form. A good example would be the recent controversial wicket of Johnny Bairstow. So what Google algorithm does here right now is it will scan through the internet. It will check for all the headlines or all the content of the news articles which might contain some key terms, such as you have Bairstow, you'll have Ashes, you'll have controversial wickets, etc., etc. So based on all these conclusions, it will take the top articles and headlines which have these corresponding characteristics and present to you in a nice and compact form, as seen in the picture, in which I've highlighted the terms. Bairstow is like consistent in all the headlines that has been presented to you. So no one in Google is actually sitting and coding an algorithm which will tell the news algorithm to look for Bairstow in all the articles. It will just use its own mind, in the sense it will just try to group all the algorithms which have a common term and club them together to form a section in the news article in Google News for you. So that's unsupervised learning. Coming to the third type, which is slightly different from others, is reinforcement learning. So what reinforcement learning does is to be broken down into a very normal level, that is try until you succeed. So the machine will do an action, and based on the action and the feedback from the environment, the feedback can be in the form of sensors, touch sensors or audio sensors, and based on the feedback, the algorithm will provide the machine with some reward or a punishment. Say you have a home cleaning robot. The robot is going around your house cleaning and it crashes into a wall at a particular place. So the touch sensor will be activated and it will punish the algorithm for going to that place. So when the next time the machine is at the exact same spot, it will try to avoid hitting the wall or giving a contact with the wall, so that the punishment is reduced and the reward is increased. So reinforcement learning is a process. It will run the iterations again and again until the point where the rewards are maximized in the least number of steps possible and the punishments are also reduced. So these are the three types of machine learning algorithms. Now I'll just have a small poll in which I've given a problem statement. You can access this using the QR code, or you can type in the code into the website. I'll activate the poll soon. Yeah, I hope the question is clear. Social media has access to user data, including the posts, likes, and comments, which is pretty dangerous in day-to-day life and a violation of your privacy, but that's what it is. So now they want to identify distinct user segments based on the interaction preferences. Basically, say Instagram, you will like a certain number of posts or a certain number of topics, and based on that, they will segregate into you into some categories. So in this type of analysis, which type of learning might be useful? Unsupervised, supervised, or reinforcement learning? I'll give some 20 more seconds. We'll see the results. I'll stop the poll now. And most of you were pretty correct. It was unsupervised learning that led the poll for 74%. So why is it unsupervised learning? So it's unsupervised learning because you did not explicitly tell the algorithm, the social media algorithm, to look for certain aspects. It will just have some raw data and it will classify you into based on your preferences. You're not telling the algorithm specifically what to look into it. So that's why unsupervised learning is employed here. Again, you can correlate it with the Google News example which I gave. It will just look for certain parameters in the data and it will classify you based on that. So I hope that was clear. Now we'll go into the crux of today's presentation, that is linear regression, which is a type of machine learning that's employed. So what is linear regression? Before that, we'll go to what is regression actually. So regression is a type of supervised learning in machine learning that helps in mapping a predictive relationship between labels and data points. That is, as you can see in the animation below, we'll have a certain data on a graph or something, and we'll try to predict a function that correlates all the data pretty well on the function, so that if you give a new input to the data, it will calculate it through the function and it will give an output based on that. A good example would be, say, housing prices. A house price, what it basically depends on, it will depend on, you will have floor area, you will have an address, you will have the number of bedrooms, etc., etc. So these are the number of features that a housing price will depend on. So based on all these features, you will set a function such that it accommodates all these features on its own, and the output of the function will be the house price that is predicted. So it'll give some inputs which have all the features and the corresponding housing price. It will map a function on its own, and then when you predict a value using the function, it should give a pretty neat output with respect to the function and the data is inputted to the algorithm. So this was regression. Linear regression would be a subset of regression models. So linear regression attempts to model the relationship between the features by fitting a linear equation to the observed data. The equation is y cap is equal to wx plus b. As some of you, most of you must have learned this in your school times. This is just a slope form of the line. So we'll break it down. Y cap here is the predicted value. That is the value predicted by the algorithm which it develops is equal to W. W is the weight corresponding to the input value. So weight is something that is a value which gives an importance to the input feature. If the weight is pretty high, that means that particular input feature has been given more importance. We will come to this a bit later in this presentation. Right now, we are just dealing with one variable. So W is the weight, X is the input value, and B is the constant value. That's the bias that will adjust how the graph is shifted upwards and downwards in this. So as you can see in the image below, we have a data set represented by the blue points. And when we run the linear regression on this, you get a straight line, straight red line that accommodates most of the blue points along with it. So as you can see, there are like, you can modify W and B as much as you want, but there has to be certain parameter which gives you an idea of how well the model is fitting the data values. So at that point, you get something called a cost function. So cost function is something that you design or that's something that's implemented, which gives an idea of how well the straight line is fitting all the data points present in your data set. That is, if the cost function is pretty high, the model that the algorithm has made is a pretty bad one. And if the cost function is low, that means the fit is a pretty neat one. That is, it's accommodating all the data points pretty well. And the output will also be a pretty close value to the estimated output value. Different types of cost functions that are used are mean squared error, mean average error, binary cross entropy and categorical cross entropy. Binary cross entropy and categorical cross entropy are used in classification models, which the second of half of today's session will deal with, that is logistic regression. Mean squared error and mean average error are the ones that are mainly used in linear regression, and today we'll deal with mean squared error. We'll go to mean squared error. Mean squared error is basically defined as J is equal to 1 by 2m summation of y cap I minus yi to the power 2. So this might look a bit daunting. We'll break it down variable by variable. So the y cap I minus yi term that is given is basically the error. That is the error calculated between the predicted value. As you might remember, y cap I is the predicted value of the algorithm, and yi is the original output that the model already has. So as you can see in the graph, the line is the model that the algorithm has made, and the data points are the input values. So the error corresponds to the difference between the predicted value and the original value that was present in the data set. And why are we squaring it here? We are just squaring it just to prevent any negative signs from popping up. As if the predicted value is more than the expected value and predicted value is less than the expected value, both of these are just errors. We don't want to differentiate based on is it more or is it less. So at this point of time, we square it just to make all the terms positive. Now we sum all the individual errors. Say there are like 10 training examples. So for individual training example, we'll sum the corresponding error and we'll square it. And then we will divide it by 2m. We're dividing it by m to just to get the average of the error to reduce the value of the total squared error. And why are we dividing it by 2? Well, it's just a mathematical operation. Dividing it by 2 doesn't have a lot of implications, but in the further steps of implementing the algorithm itself, the 2 will help reduce down the calculations even more, as I'll show in the next few slides. So when you plot the mean square error graph as a function of w and b, here theta1 corresponds to w and theta0 corresponds to b, it is just a notation. You will get a nice parabolica type in graph with just one global minima. I hope the difference between global minima and local minima is pretty clear. We'll have just one minima. That is, there will be only one value corresponding to w and b, where the cost function will be at its minimum, right? So at this particular point, the cost function will be at its minimum. As I told earlier, minimizing the cost function will give you the best fit line for a data set. So what's the advantage of having just one global minima and not a lot of local minima as shown in this image? I'll show them. As shown in this image, well, at that point of time, your gradient descent algorithm. And what is that? I'll explain in the further slides. It's an algorithm which is basically used to find the corresponding values of W and B at which the cost function is at its minima. So put in a very layman terms, what you actually do is you stand on the function, you take a look around you. Actually, you turn around and you look in all the directions and you find that particular direction in which the slope is at its highest in the decreasing manner. That is, at one particular direction, the function will decrease the most rapidly, right? So in that direction, you will take a small step of a distance, say alpha. You will take a small step in that direction. We'll stop there. You will again turn around in all the directions. You will again check the slopes in all directions and will determine the direction which has the highest slope in the decreasing order. You will find the direction. You will again take a small step of value alpha. You will again reach a point and you will so on. You will continue this. And as you carry on with this algorithm, you will eventually reach the minima of the parabola. That is, we will reach to the point corresponding to W and B at which the cost function will be at its minima. That is, the line, the Wx plus B that has been made by the algorithm is at its best fit and has the least error between the predicted value and the original value that has been given input to the algorithm to train its model on. So why mean square error is a good algorithm for cost function? Well, as you can see in this image, the algorithm will start at a random point and then it will try to navigate to the closest minima. And an advantage of mean square error is that there is only one minima and that is the global minima. For some cost functions, the cost function, when you plot it, it has several minimas along the way. So the gradient descent algorithm might reach a minima, which is a local minimum, but not the global minima. That is, it will not reach a point where the cost function is actually at its highest minimum value, at the lowest value possible, corresponding to W and B. So in this manner, gradient descent algorithm applied on mean square error is one of the best implemented algorithms. So to put in mathematical terms, all these notations might seem a bit daunting. We'll again break it down step by step. So here, one thing to note in the first line is that the equal to sign which has been provided here is not an equality sign in mathematical terms, but it's rather an updating step. That is, the RHS is implemented in the value of LHS. So the W gets updated to the value of the RHS. So we'll take the left-hand column first. So W is equal to W minus alpha times del J by del W. I hope the calculus part is pretty clear. Del J by del W is just we're differentiating the cost function with respect to W. So again, as I explained, we are just going to find the direction in which the slope decreases the most, and we are taking a small step in that direction. So that's what the algorithm basically does. Alpha is the small step we are taking in staking, and del J by del W will give the direction will give the direction in which the slope decreases the most. So we are updating W by a value which is alpha times the highest slope in the decreasing fashion. So when you apply calculus, del J by del W comes out to be 1 by M times summation of y cap I minus yi times xi. So here you can appreciate why when we're defining the cost function, we use the term 1 by 2m. So when we apply the chain rule and the differentiation rule, the square terms comes down and it cancels 2 from the numerator and denominator. So it gives a pretty neat function. So y cap I minus yi is the error term, and the xi term just pops up because W term had a coefficient of x, if you remember. Y cap I was defined as wx plus b. So that coefficient of wx comes when you apply the chain rule during differentiation. So when you again substitute it, you get w is equal to w minus alpha, the mean of summation of the predicted value minus the original value multiplied by xi, and you multiplied by the alpha term, which is the small step which we take in the direction of the highest possible slope. Well, coming to the b term, b is again, it's the same algorithm. Instead, we don't have the xi term because b is a constant and you don't have don't have a coefficient going along with it. So you don't need to apply the chain rule again, and you'll just get a simple term. B is equal to b minus alpha, which is the into multiplied by the average of the original values minus the predicted values. And this you need to repeat until convergence. By convergence, I mean at a particular point of time, the W won't get updated again and again because the W and B has reached the minimum of the cost function and the slope becomes 0 at that point. So essentially your first equation on the left side, that is del J by del W, that will become 0. So W is equal to W. It will keep getting updated by the exact same value. So it doesn't exactly make any sense. So you need to repeat this process till convergence. Word of caution, both W and B terms need to be updated simultaneously. That is, you need to update W, B, and then you have to proceed to find the new iteration of the cost function. Because as you can see, updating values of W and B use cost function, and the cost function again involves the parameters W and B. So you need to update them first. Then in the next iteration, you need to find the cost function. Then again in the next iteration, use the cost function to update the values of W and B. So there was a term called alpha, which I mentioned it as the small step which we take in the direction of the highest slope in the decreasing manner. So alpha is a hyperparameter. Hyperparameter is something that we set as users while training the model. That is, it completely depends on us. This is not something the machine will learn over time. So there can be two possibilities. Either your alpha is small or your alpha is pretty large. So what does a small alpha signify? You will start at a point. You will take very small steps in the direction of the highest gradient possible. So what this will signify is your algorithm will always reach a minima, which is pretty much guaranteed because your alpha is pretty small. But the convergence time might take a lot because again your each iteration the algorithm will update by very few amount. So the time taken to reach the minima might be a lot compared to a normal alpha, which you might set. So you might think, okay, let's just increase the alpha, which is a nice solution. But if you increase the alpha a lot, the algorithm will actually overshoot the minima. That is, it will reach the end of minima and your alpha will be so high. That is, the step which you will take will be so high, it will cross the minima and it will overshoot to the opposite side. And this will keep on fluctuating between one side to other side, and your cost will actually start to increase after each iteration. So this is another issue which we don't even need. So a small alpha will give a short method of reaching convergence, but it will take a lot of time. But a very large alpha, what it might do is it might start increasing your loss after each iteration. So that's something you need to keep in mind. So a good practice is you can plot using matplotlib loss and the loss function with each epoch. Epoch is basically after each updating step. You can plot the loss function on a graph. And if your graph is converging very slowly towards zero, that means your alpha is pretty small. You can increase it a bit. And if the loss function is actually increasing a lot, that means your alpha is also pretty large and you might need to reduce a bit so that it reaches the convergence point. So we'll now move to code implementation of the linear regression. We'll use a library called scikit for that. That's one. And also we'll first try to start from NumPy, which was taught in the earlier session. We'll try to build it from scratch itself. Then we'll move to the library, which will directly implement the linear regression model. I'll take some questions now, if there are any question that has been put. Okay, so there have been no questions in the Q&A section, so that's pretty nice to see. I'll share the linear regression screen now. I hope my screen is visible. Yeah, I'll zoom in a bit so that it's easier for you to guys to see. Okay, so we'll first look at how to implement linear regression from scratch. That is using only mathematical terms instead of importing any machine learning libraries. So we'll import pandas, we'll import matplotlib to plot some graphs, and we'll import NumPy, which will basically assist us in help modifying the data set. So we'll import them first. And now I have a data set, which is some random collection of 100 numbers. I'll print the data set for you. It's basically a column. 0th column has some numbers and the first column has some numbers. And here you can see data is equal to pd.read underscore CSV and header is equal to none. So header is equal to none basically shows the fact that we don't have any headers in the dataset itself. There are no heading line called rows in that. So now what we'll do is we'll set an array X, which will take the first column of the dataset and Y as the second column of the dataset. As you might remember, indexing always starts from 0 in computers. So X will be data 0 dot values, which is like the first column, and Y will be data 1 dot values, which will be the second column. And now we'll plot it again. Arrow will be red dots X and Y on the graph. As you can see, this has some slight linear pattern to it. So it's a good indicator that we want to use linear regression on this. So just to revise, del J by del W will be 1 by M times the summation of predicted values, the error times Xi, and del J by del B is equal to 1 by M times the error values summed throughout. And the cost function itself is 1 by 2M, the error squared through all the values in the dataset. So now we'll start implementing the linear regression model itself. So number of iterations is equal to 50 is basically the number of times you want to run the gradient descent algorithm. That is how many steps you want to give it to reach the minima itself. This is again a hyperparameter. You can increase it to a lot so that you give it a lot of time. You give the algorithm a lot of time to reach the minima. And you have learning rate, which is again a hyperparameter as I explained, which is basically alpha. You might want to change this, increase this or decrease this based on how your cost function behaves over each iteration. Now we'll initialize the parameters M and C. M and C is again basically W and B in the terms. I'm just using M and C because it's used in the slope form of line y is equal to mx plus c. And now we'll introduce three arrays, history underscore cost, m underscore history and c underscore history. basically these three will keep track of cost function, the value of m, and the value of c over all the iterations possible. So this will, when you print it, you'll get an array of size 50, which has all the data stored in it. So now we'll run the model. So we'll predict the volume. We'll predict the values. Y pred is equal to mx plus c. And now we'll calculate the error. Error is again y pred minus y, which is basically this term over here, y cap I minus yi, as cost function was defined as half of np dot mean time error square. So what we're exactly doing here is we are squaring the error, the square term over at this place, y cap I minus yi whole square. Then np dot mean will basically calculate the average. That's what 1 by m times the summation will do. And we're multiplying it by 0.5 to signify the fraction half over here. So this is the cost. And m deriv is basically your del j by del w value over here, which is again the average of summation of all the errors multiplied by the x term. So that's what we're doing here. We have m derivative is equal to mean of the y pred minus y multiplied by x. And again, you have c deriv, that is del j by del b. That's the average of all the errors summed together. So c is again, c is equal to c minus, c deriv is equal to np dot mean multiplied by the error value, that is y pred minus y. And now here again, we're simultaneously updating both m and c. That's what I mentioned here. Before going to the next iteration, we're updating both m and c values so that the cost function in the next iteration will use the new updated values of m and c to prevent any errors from popping up. So m was again, m is equal to m minus learning rate multiplied by the derivative of del j by del w. And c is equal to c minus the learning rate of c into learning rate and the derivative. And now we'll just append the cost function into the history.cost array. We will append the m value into the m.history array and the c value into the c underscore history array. So we'll run this code now. And as you can see, the model has predicted that a line with a slope of 1.47 and a constant value of 0.03 best fit model for this particular data set on this line. So we'll now plot the cost function for each iteration. And as you can see, the cost function reduces dramatically in the first few iterations itself and then stagnates over a period of time. So this indicates that a learning rate was a pretty nice fit. And we don't need to update the learning rate or increase it or decrease it, as it is the cost function has reached its minima. And also this indicates the fact that changing the number of iterations at this point, that is, it was at 50, but as you can observe that it's stagnating at around 10 to 20. So decreasing the number of epochs will reduce the runtime for your model training. Here it might be 0 seconds for now, as the dataset was pretty small, but when you increase it, when the dataset is actually pretty large, then you might have to print the cost function for each iteration, and you might want to reduce the number of iterations to increase your computing speed. So now we'll plot the line and the dataset together. And as you can see, it's a pretty neat fit for the dataset which has been provided. All the points above and below the lines are equally distributed. So the error for this particular will be at its minimum. So now I'll show how the algorithm actually ran. We'll use the, what do you say? At this particular point, we're using matplotlib to plot all the lines, as it was discussed by Shrikar a few minutes ago. Now we'll just animate this algorithm and how it iterated over all the 50 iterations. So as you can see, it starts from w is equal to 0 and c is equal to 0. It starts at a horizontal line. And then after each iteration, it tries to adjust itself to the data points so that the error is minimized for that particular iteration. And it applies the gradient descent algorithm. So as you can see again, after pretty much 10 to 15 iterations, the error is minimized and the cost function reaches at its minima. So it's a pretty decent fit for this. So now this was implementing machine learning right from the scratch. That is, we are using all the mathematical terms. We're even describing how to differentiate it using general calculus, which might not always be the best scenario. So now we'll use, as you can see, I used 9 cells. Cells meaning the 9 sets of code which I used. I used 9 cells to implement using Scratch and using scikit. Scikit is basically a library which has all these algorithms already coded in itself, and it takes only one cell to use that. So again, we are importing np as numpy as np, where you from sklearn.model. This is the library. we are importing the model linear regression from it. So again, x is equal to np.array data.ilog in the 0th column. That is, we're assigning the first column to x and we're reshaping it to -1, 1. So what it essentially does is it converts this x into a 2D array. This is something which the sklearn model requires. This is not a mathematical implication. So this is just a part of the algorithm. And y is the first column. And model is linear regression. We are fitting both x and y into the linear regression model. And that's it. It only takes 3 to 4 lines of code to implement linear regression using scikit. And now we'll print the intercept, that is b. We'll print the model coefficient, the slope, that is w. And then we'll just plot the line to see how well the data line fitted the model. And that's a representation. So again, the implementation from scikit might look pretty simple, but I'll again urge you to take some data set from online and then try to implement it from scratch to get the gist of what's the mathematical linear regression model is, and then move on to scikit so that any modification which might arise from the dataset itself, you can easily tackle it using a mathematical skills rather than depending on a scikit or a library. So that's linear regression for now. If you have any doubts, you can unmute yourself. You can raise your hands. You can then unmute and ask. Okay, I'll once check the. Could you explain code implementation again? That might take a lot of time. We'll move on to polynomial regression for now.
Yeah, the person, whoever is asking that, right? Like, if you can be more specific, that will be more helpful.
Yeah,
because
exactly.
Going through the entire code will be difficult. If you are not clear about any specific part, then you can mention that so that Shailesh will be explaining it again. And also, guys, the people who are attending the session from YouTube, we have shared the G form for attendance. So you can start filling the G form. Yeah, over to you, Shailesh.
I'll move on to polynomial regression. This doubt came on Slido. So if you can be a bit more clear on what exact problem you face in the code implementation, I'll take it in a few more minutes.
Can I ask Mero?
Yeah, sure. Go ahead.
Yeah, I have a doubt. When you're iterating through the dataset values, how exactly are you doing that? Like you just have the variables y and x in the cost and error portion. How are you iterating? Like where are you specifically iterating through the dataset that you're using?
I'll open the code. I'll explain it to you. I hope it's visible. Yeah.
Oh yeah, the screen is visible. Yeah.
Yeah, I'll go through it. So here, so this is the predicted value, right? The y cap I is the mx plus c. And here we're calculating the error. So this will create an array. Y pred will create an array of the value mx plus c, and x was already an array here, right? X is an array.
That is my question. Where are you? That is my question. Where are you iterating through the values of y and x, like only y and x in the code?
No, see, I'm getting the y pred value here, and here I'm calculating the error, right? Iterating, yeah. I think here, there's a for loop here. I'm iterating through 50 times. I'm calculating the error. I'm calculating the cost function. I'm now calculating these derivative terms using maths. Right?
Yeah.
And now I'm updating the m values and c values based on these derivative terms. And then I'm running the loop again. So here, the m and b values will get updated. And when you run the loop next time, the y pred value will get updated using the new m and c terms. You understand?
Yeah. Yeah.
So when you run this again and again, the y pred values will get updated using the previous iteration of m and c. Then your error will get updated. Your cost function again will get updated using the error value. So this loop will go on again and again. I hope it's clear now.
Yeah.
Yeah. Right. Any more doubts? We'll move to polynomial regression now. Before that, I have another small poll. You might join by scanning the QR code or type in the code over here. The poll should be live now. The question is, we're applying gradient descent algorithm on the mean squared error. It's observed that it fluctuates around the minima without converging. So what can be done to resolve this issue? The options are decreasing the learning rate, changing the cost function to MAE, that was the mean average error, and increasing the learning rate. We'll stop the poll in about 10 more seconds. Okay, as most of you have mentioned correctly, it's decreasing the learning rate. So why is it jumping around the minima? Because your alpha is too high that when it comes near the minima, the next step which it takes, it is too high that it crosses the minima and goes on to the other side of the graph. And again, the slope will be of the opposite sign. So when you have a high alpha, it will again fluctuate to the opposite side. So decreasing the learning rate will give it a much more slower path which it will take to reach the minima compared to increasing learning rate or changing the cost function to MA. That's just a fun option which I put in that doesn't relate to this. So decreasing the learning rate will give you a much faster, a better convergence at this point of time. So we'll go to polynomial regression. So as the data set which I provided,
yeah, I have another small announcement. So many of you are asking why isn't the link posted on the WhatsApp groups? So let me repeat it again. The Google form for attendance is specifically only for the people who are attending the session from YouTube. So we are posting it only in the YouTube live chat. For the people who are attending the session on the MS Teams, your attendance will be automatically recorded. So you need not worry about it. Yeah,
continue, right?
Shailesh, you can. Yeah, you can continue.
Yeah, okay. So the data set which I had taken during the code implementation, that had a pretty linear vibes to it, right? But in the polynomial, sometimes the data, like most of the times, the data might not be a straight line fit, which pretty much captures the essence of the data. You might think that a polynomial, okay, an x squared term or an x cube term, x cube function might be a better fit for that rather than a straight line. So this is what polynomial regression basically does. Again, your input parameters will be only two variables, that those will be x and y. Y will be the corresponding value to the x will be the input and y is the output. But what the algorithm will do is it will create more features. That is, it will create x, it will create a column for x square, it will create a column for x cube and so on. So essentially, when you have a function, it will be a polynomial function of a degree which you as the model setter will decide. So this is called polynomial regression. And say there are 10 data points and you set the degree of the algorithm to 10. So using basic mathematics, obviously the algorithm will fit through all the 10 points. But this is another issue which comes up when you start increasing the features, which are called overfitting and underfitting, which needs to be addressed while implementing polynomial regression. So as you can see in the image above, you have a data set which is not at all linear and pretty much indicates that you need some higher features at this point of time. But when you try to fit a linear model, it's basically underfitting. Underfitting in the sense that it's not capturing the data points pretty well. And also, one thing to note is that this data model might also have gone through the same cost function and the same gradient descent algorithm. So this particular fit of the linear graph will be the graph with the lowest error possible, but the error itself will be very much high. But so what it's essentially doing is doing the best out of the worst possible outcomes, right? So you might think, okay, let me add a feature now. Let me add a feature of x square. So your function will be of the form ax square plus bx plus c. It might give a pretty neat fit. You will add one more feature called x cube. So that might give a good fit, robust fit. That is, it is going nearly going through all the points, but it's not trying to touch all the points individually. That issue might arise when you think, okay, I'm increasing the features and my accuracy of the model is increasing pretty well. So what I might do, I might just keep on increasing the features and try to reduce the error to absolute zero. That is, the function is neatly plotting all the data points which are provided in the data set. So that's called overfitting, or in another terms, it's called high variance. And the underfitting, it's called high bias. Bias in the sense it's not capturing the data properly. And high variance means it's capturing the data too well. Too well in the sense it's capturing patterns which are very much unnecessary while training the model. So high bias, again, you are setting the model is inaccurate in the sense it's not fitting all the data points properly. So your output will be pretty much inaccurate and the pattern of the data is not visualized properly. What high variance will do is it's capturing all the training data pretty well. But if you give a new input to it, the output might be pretty much ridiculous at that point of time because the curves might be so steep and the function might be too complex that the output might be too bad just to fit the data points in the algorithm. One more thing to note is that if we slightly tweak the input algorithm, input dataset itself, that is, say if you change the y value of a corresponding x by say +5 or -5, the output function might be completely different at this point of time because the algorithm is heavily trying to fit all the data points into the function. So the model itself is pretty much untrustworthy at that point of time. So how do we deal with this factor? What you do is, a good practice in machine learning always is, if you have a huge data set, we split the dataset into two types. One is called training dataset and another is called testing dataset. So usually we keep the ratio as 9:1, where 9 is the training dataset and 1 is the testing dataset. So what we do is we train the data on the 90% of the dataset, and then using the test dataset, we input the values, we get the values back, and then we calculate the error which we already have. I hope that's clear. The 90% is used for training and the 10% is just used to test the accuracy of the model based on unseen data before it's being implemented on some large scale data sets which you might have, to which the model is used to predict the values for. So when you plot the error versus the model complexity in the sense you can plot for each power of x, that is, you're calculating error for say a linear graph for x square, for x cube, for x, for x to the power 4 and so on. You might plot the error for this. So what the algorithm will do is, as the complexity of the model will increase, your error will start to obviously decrease, because as the degree of polynomial will increase, it will obviously try to fit in more number of points in it. So till one particular point of time, the test error of the algorithm, that is the error generated by the test data set, which the algorithm has not seen now, the error will also decrease till that point. That is, till that particular point of time, the algorithm is doing pretty well trying to understand the pattern which we want the algorithm to find out. But after a certain point of time, the training error will keep on decreasing because again the model is trying to plot, is trying to get in all the data points possible, but the test error will start to increase, right? Why is that the case? Because the function is too much complex to give a good valued output for this. This will be pretty much clear when we go to the code implementation of polynomial regression. So that again, we move to code implementation for this. I hope my screen is visible now. So for polynomial regression, we'll again import the basics. We'll import numpy as np. We'll import matplotlib as plt, and we'll import from sklearn. We'll import linear regression, and this is pre-processing. Why is this? See, linear regression is the model which we are implementing here because the weights are just a linear combination of all the features that are being inputted. So importing linear regression from the linear model, and polynomial features is pre-processing. Why is it pre-processing? Because we're inputting just x and y. But the algorithm, before it starts to apply the linear regression model, it will create some new features. It will create the polynomial features. That is the x to the power 1, 2, 3, 4. extra arrays it will create from the polynomial features model. So we'll run this code. It's connecting to the CPU. So we'll run this code. And now we'll generate a random 2D array. Why 2D array? Again, because linear regression from sklearn requires a 2D array for it. So we are doing x is equal to 4 times np.random.ran 100, 1. That is, we are creating an array of the dimensions 100, 1. We're multiplying it by 4 and we're subtracting 2 from it. So np.random, and then we're doing y is equal to 4 plus x plus 2x squared minus 5x cubed. So basically, we're defining a function from our own side. We're creating a data set which nearly closely follows the data set. Plus, we're doing np.random.random of the array size 100, 1. So basically, this term is used to generate some noise in data set. So we're creating y, which closely resembles a function which are already determined just to test the data set. And then we're doing np.random to add some noise into it. And now poly features is basically polynomial features of degree is equal to 3. We want a degree 3 to be fit into the curve because we are defining the dataset itself as a degree of 3. And then we are fitting x poly is equal to poly features dot fit and transform x into something of arrays x, x square and x cube into x poly. And the regression is again linear regression. Why is it linear regression? Because again, it's a linear combination of the weights. We are not changing the weights into something w and w square. We're just introducing new features of x and x square. And then we'll fit linear regression to it and we'll fit x poly and y to it. So a0 will be the constant term, which will be the intercept. A1 will be the coefficient term, that is x coefficient. A2 will be the x square coefficient. And A3 will be the x cube coefficient. And then now we'll plot this using x and y. And x will be the data set of x. And y will be the a0 plus a1x 9 plus a2x square plus a3x cube. And now we'll plot this. As you can see, it's a pretty decent fit for the algorithm which we based. So that's all. Polynomial regression takes that much time. And now we'll go to what I meant by bias and variance trade-off. So we'll import numpy's np. We'll import again matplotlib. This is an interesting line of code, that is np.random.seed, bracket 0. So what it does is, whenever we use the random function from now on, at the first iteration, it will generate a random data set based on your requirements. The next time when you run the code, instead of creating another random set, it will generate the exact same random set of data again. So this is pretty useful when you want to run the code again and again to show the data set being constant over the time, but the first iteration will be completely random. The second running of the code will generate the exact same random data set. So now again we'll generate x as some random data and y as a function of x square and x cube plus some random. So np.random.normal, what it does is it will add some noise of dimensions 20 because we're adding dimensions 20 here, 20 points in the sense. And the -3 indicates a mean of -3 and a standard deviation of 3. So people who are familiar with standard deviation data set, so this will create a standard deviation data set with -3 being the mean and 0 being the mean here to generate some noise. And 1 will be the standard deviation of the data. So we'll plot this to see how the graph looks. So this is the data point, and as you can see, it gives a slight x to the power 3 vibes to it. So now we'll try running linear regression to it. Again, we'll import linear regression from sklearn model. We're again importing the mean squared error and np.random.seed, we are setting it to 0 again, just to generate the exact same random data again. This again, we're setting it so that the exact same data set is generated over in this point of time also. And we're transforming the data to include another axis, that is x is equal to x.np new axis. Why are we doing this? Again, as I previously mentioned, linear regression from sklearn requires a 2D array. So we're just adding a new empty array to x and similar to y. And we have model is equal to linear regression. We are fitting x and y to it. And y prediction is the model.predict. That is, it will predict y predict from the input dataset x. If you want, you can print y pred. I'm not doing that because I don't want to print 20 values of y over here. And now we plot this. And as you can see, it's a pretty bad fit to the line. That is, the data sets are pretty much scattered all over the place and it doesn't capture the pattern of it. So we might think, okay, now let's add some feature to it. Let's add x squared to this. So now we'll, from sklearn pre-processing, we'll just import polynomial features also. np.random.seed 0 again. We'll generate x, we'll generate y. We'll again add some new axes to it so that polynomial linear regression model has the 2D array for it. Now polynomial features will fit with the degree is equal to 2 as we want a new feature of x squared to it. And again, we'll fit x poly as with polynomial features dot fit. We'll transform x into x and x square. We'll again use model is equal to linear regression. We'll fit model with y, that is from the original data set. And we'll use x poly for this, that is x underscore poly. And now we'll again plot this using matplotlib. And as you can see, the model is improving over time. That is, it's slowly trying to go through all the points. And x square also seems a pretty decent fit. Now we'll run the exact same algorithm again, and we'll just add a degree of 4. That is, the only change will be degree is equal to 4 over here. We'll run this code. And as you can see, this looks a pretty good and robust fit. That is, it's not going through all the points as such, but it's an equal distribution above and below with a minimized error. So this, as you can see, is what we call a robust fit. And the linear regression is what we call an underfit and a high bias place. So x to the power 4 looks a pretty decent fit for this. Now let's change it to degree is equal to 10, just to see how variance looks like. As you can see, this is a classic sign of overfitting. That is, as you can see in the values between x equal to -4 and -2, the slope of the graph is changing pretty much drastically over the place. So any prediction at this point of time will be completely useless. It might show that the value is decreasing, but the general trend is that the value is decreasing as x increases or x increases, y increases as x increases over a period of time. So this is overfitting and we have high variance over here. Now let's just try 20. We are setting the degree is equal to 20 and the rest of the code is pretty much same all over it. And this is again a pretty much very high degree of overfitting over here. The model has learned the data points pretty much very good. That is, it's fitting nearly all the points to it. But again, the function produces pretty much erratic. That is, if you have a degree 20 function and you have 20 points, essentially the function can, if it wants, it can fit all the data points to it. But again, you have inconsistent functions all over the place. So the output value, that is the consistency of output, if it runs some test data set to this, the error will be pretty much high. So again, that I will leave to you guys. You can play around with this. You can separate data set into test and training data set. You can then print out using matplotlib the cost function over each complexity of x to see that which is the best fit complexity for this. And as we define the y to be as something of x to the power 3, so the degree 3 and 4 would be the best fit model for this particular data set. Rest and all, if it's a completely random data set, it's always a good practice to plot cost function as a function of the degree of the polynomial, and then plot the error of both training data set and test data set for each degree to get the best plotted degree for your data set. So that's polynomial regression and bias and variance. Any doubt till now, you guys can raise your hands and unmute yourself. I'll take the doubts. Okay, so there are no doubts. I will end the linear regression and polynomial regression with just a small quiz. You can scan this QR code to access the quiz and join using this code. I'll start the quiz now. The question is, consider a data set with two variables x and y. You want to perform polynomial regression to fit account to the data. Which of the following statement is true regarding the polynomial regression? So yes, the majority was right. Polynomial regression can model nonlinear relationship between x and y by introducing additional polynomial terms of x, and that's the correct answer. The first option is wrong because that's the essence of polynomial regression. You want to fit a function which is non-linear in nature so that you can add features of x, degrees of x. We'll move to the next question. The context of machine learning models, what's the relationship between bias and variance? So yes, as the majority was right, bias refers to the error introduced by overly simple models, that is underfitting case, while variance refers to the error introduced by overly complex models, that is overfitting. So again, we have to find a trade-off between bias and variance so that your model fits the model decently enough so that your training error and your test error is at its minimum. So that's all for linear and polynomial regression. I got one doubt. How do we get polynomial features if we are implementing polynomial regression from scratch? So basically, if you say you are setting a polynomial of degree 3, so instead of having your function defined as y is equal to wx plus b, your function will now become y is equal to w1x plus w2x square plus w3x cube plus b. So you have three weights over here. And now you have to differentiate the cost function with respect to each of the weight. You will have to calculate the cost function with respect to all the three weights. And then you will have to update this cost function with respect to each of the weights on its own. So essentially, instead of having only one W, you'll have three Ws which you have to update simultaneously. So that will be the only difference while implementing polynomial regression from scratch. That's actually a nice practice method to get to know if you actually understood how to implement linear regression. How did you set the parameters? Okay, so parameters is something which you determine on your own. I set the learning rate as 0.001. And when I printed the cost function over number of iterations, the convergence was pretty nice. The learning rate was fine for that iteration. And then the number of iterations itself is again your wish. If it's 50 was a random guess, and as the plot showed, I'll just show the plot again if it's possible. Yeah, as the plot showed, the convergence, it reached the convergence within the range of 10 to 20 iterations itself. So again, 50 was a nice guess. Even I can set it to 500. It's not an issue. But again, it's just a waste of computing resources. Again, wait. Yeah, I need to plot this also. Again, it's a waste of computing resources. Your value is getting stagnated between 10 to 20. So why do you want to iterate it to 500 times? So again, the best way to do is experiment it with different values, plot the cost function number of iterations, and then make adjustments along the way. So that's how I set up the cost function hyperparameters. And there are a lot of functions in NumPy matplotlib. So how to keep track of all of this? No one even in our AI club knows all the functions pretty by heart. I would always suggest go through documentation of each of these libraries, or you can even search up Google. But you should know what are trying to achieve with these libraries to get the exact syntax values, and that's why these are important. So I'll close the session on linear regression and polynomial regression. Hope you guys understood it. We'll have a 10 minutes break. We'll come back by around 6:35, and then Pratosh will take on logistic regression, which is another type of regression used in classification models. Thank you.
To those of you who have asked where the data.csv file is, it is uploaded to GitHub now. Under session 2, you will find data.csv. You can download it there.
Also, guys, hold on. Don't leave the session. We are not done yet. We are having a 5 minutes break. At 6:35, we'll be again starting with the second half of the session, which is logistic regression. So till now, we have looked into regression models. Now we'll be looking into classification models. So hold on for another 2 minutes until we begin the session again.
Okay, a bunch of you are asking how to do task one again and again. I'll repeat myself at the end of the session. We will explain how to do task one. I will clearly explain what to do with the data set. I'll explain how to upload it to a collab notebook and how to work with it. Don't keep messaging now. Okay, another doubt came up where how to check GitHub dataset link again. We'll go through it one more time. If you see my screen, this is a summer school presentation. This is the summer school repository. Under session 2, you will find a data.csv. Click on that, you will be able to see the dataset. Here there will be a download button. You can download the file. After you download the file, you have to upload it to a collab notebook where you will see this folder. Okay, it's connecting to the runtime. You will see the folder, then you will see a file upload page, which will look like this icon. When you click on this, you should be able to see a pop-up and you can click on the data which you have just downloaded and you can upload it here. This is how you do it. Any further doubts, we will take it after the session.
Pratush, I guess you can start.
Okay. So well, I think my screen is visible and audible.
Yeah,
Yeah,
you're clearly visible and audible.
Fine. Okay. So hi guys, I'm Pratush, and today I will cover logistic regression, which is also another powerful supervised learning model, which is used for classification problems. So far, we have seen linear regression and polynomial regression, which is used to predict a number. So they can be useful in problems where uh, we predict certain number. Like let's say you want to predict the price of a house given its features like the square feet area, the number of bedrooms, and then the number of floors it consists. So for all those kind of problems, we can use the linear regression and the polynomial regression. There's also another important problem that we face in real life, which is a classification problem. So a classification problem is where we try to categorize a given sample into three defined classes. So let's say you have an email. You can predict or whether it's in spam or not spam, and you can classify it into two predefined classes. That is spam, which is the positive class, and not spam, which is the negative class. These kind of classifications where you have two classes, we call it a binary classification problem. When you have three or more classes to classify, we call it a multinomial classification, just like a cuisine preference, like Indian, Chinese, or Italian. If we have classes which have certain kind of relation between them, like let's say, the 5-star ratings that you give to an electrical appliance, or the customer satisfaction report in a restaurant, you have classes like low, medium, high, or 1-star, 2-star, and all the way up to 5 stars, where there's some kind of relation between them. So you cannot get a 3-star rating without satisfying all the requirements for a 1-star rating and a 2-star rating. So in that case, it's an ordinal classification problem. So can we use linear regression for classification problems? It turns out that linear regression fails badly in a classification problem. It does work sometimes, but in most of the cases, it fails. So we'll take an example and we'll see why it fails. All right. So we'll take a simple example where we try to classify a person as obese or not obese given his or her weight. So let's take some data points. Let's take some data points like this, where you're given the weights of them. Let's say you have 45 kgs, 50 kgs, 55 kgs, and 60 kgs, and we label each of them as 0, which indicates that they belong to the class not obese. Okay. Similarly, we take another set of data points for the class obese, which is denoted by 1, and we take 90 kgs, 95 kgs, 105, 110, and we label each of them as 1. We'll use different marker styles to differentiate the both of them. And if we plot them, we have some kind of a data set, which you can see that they lie between 0 and 1. Now, we'll try to fit in a linear regression model. That is, we'll try to fit in a best line. That is, we'll try to find a best line fit to predict to which class each of the corresponding weights belong to. We'll import the linear regression model from the sklearn library, just like we did before. We'll take the same data points. We'll concatenate into a single set. Similarly, we'll concatenate all the labels into a single set, and then we'll feed it into the linear regression model instance that we have getting using the dot fit method. Now we'll generate some predictions for a set of x values or a set of weights. So we can generate set of weights from the minimum of x to max of x using the line space function. So what this does is it generates 100 weights, 100 values between 45 to 105. Okay. And then we'll have a y predictions which are made by the linear regression model using the dot predict method. We'll also choose a threshold value. Like let's say if your model predicts any value above 0.5, you say that it belongs to the class 1, or you classify it as obese. Or if your model predicts any value below 0.5, you will classify it as not obese. So this 0.5 is a thresholding value. It's a hyperparameter. That is, you can adjust it according to your need. We'll see how adjusting the threshold value has an impact on the accuracy of a model later in the session. So for now, we'll set it as 0.5. And one more important thing is that in any classification problem, we try to predict a probability of a given sample of it belonging to a certain class. So let's say your model predicts 0.6 as the probability for a given weight. Let's say you are inputting the model some 50 kgs. Then your model predicts some value like 0.3. So what it means is that it means the 50 kgs person belongs to the category obese by a chance of 30%, and the remaining 70% can be belonging to the class not obese. So that's how it works. So if your model predicts any value above the threshold value, you classify it as the positive class 1, and if it's below, you classify it as the negative class 0. So let's fit in the linear regression model line and also the threshold line. If you look into the plot we have made here, the red line is your best fit line, and the black vertical line is your threshold line. So we have classified the data points correctly as the two classes, obese and not obese. Now let's say I take some more survey, and I get to see that there's another person with a weight 85 kgs, and he turns out to be not obese. Okay. Now our model should be classifying this guy with a weight of 85 kgs as not obese according to the ground truth value. Let's see if it does. So if you run the code, you'll see that even though that this person indicated by the blue model, which indicates not obese, the linear regression model that we have used predicts that it belongs to the obese class. So that's why you see that linear regression is not a good model for classification problems. This is because a linear regression model would predict a number, a value between -infinity to infinity for any value of x. So it does not have a specified range between 0 to 1, where we want our probability to lie, because we know that probability always lies between 0 to 1. So what we need to do is, how do we solve this problem? We need to come up with some other function whose range is between 0 to 1 for all values of x. So we'll look into that. So one such function is the sigmoid function or the logistic function, whose range is between 0 to 1 for all values of x, as you can see from the graph below. And one more thing is that you can notice that at x equal to 0, your y value is nothing but 0.5, right? So the sigmoid function really achieves the problem of the range of your predictions. So using this, we can build the logistic regression model. So the formula for the sigmoid function is given by g of z equals 1 by 1 plus e power minus z. So what we do in a logistic regression is that we simply take the output of a linear regression model and apply the sigmoid function to it. So the input to a sigmoid function is nothing but the output of a linear regression model. So the linear regression model here can be expressed as wx plus b, that you put inside a sigmoid function and you get the probability between 0 to 1. We'll go back to the same example that we saw earlier, and we'll see how logistic regression excels in a classification problem. It's a linear regression field. Okay, so we'll take the same data points that we used before, same 45, 50, 55, 60, and then same as for the positive class. We'll do the same thing, but just one small change. We'll try to fit in a best S curve, which is the sigmoid curve, rather than a best fit line. We'll import the logistic regression model from the sklearn library. We'll also look into the implementation of logistic regression from scratch later, but for now, we'll just import it from the sklearn library. We'll do the same thing. We'll make an instance for the logistic regression model, and then we'll try to fit in x and y. Then what we'll do is we'll make predictions for the same set of 100 weights that we generated between 45 to 105 using the dot line space method, and we'll find the predictions made by the model for each of the corresponding x curve values. If you plot the graph, you will see that the logistic regression also classifies the data points correctly, just like how linear regression did initially, for a threshold of 0.5. You'll be using the same threshold of 0.5 here also. We'll do the same exercise of adding another weight or another person's data, as we'll add another person who weighs 85 kgs and is also not obese. Now let's see if logistic regression can classify this person as not obese. As you can see here, even though the new data point which we added is an outlier to the rest of the not obese group, the logistic regression model is able to classify it correctly as not obese. And the rest of the area, or rest of the data points which lie to the right of the black line, which is your threshold line, is labeled as obese. So that's why a logistic regression model is able to, or it excels in the classification problems, because it always tries to give you a value or a probability between 0 to 1, which is what we want. We'll go back to the slides. we'll talk about decision boundaries. So the black line which you saw in the demo is your decision boundary, which is the line which separates the two classes, the positive and the negative class. So what we do is, let's say we have a threshold of 0.5. To get a final prediction of 0 or 1, which is your y value to be 0 or 1, we have the threshold as 0.5. And then if your f of x, which is your prediction, is greater than 0.5, you predict it as y equals 1. And if your f of x is less than 0.5, you predict y as 0. Now take a look at the graph of the sigmoid function. If you want to get your f of x to be greater than 0.5, you need to have your z values to be positive. So if you plug in z equal to 0 in your sigmoid function, that is g of z, you find that g of z equals, or g of 0 equals half 0.5. So for any value of g of z to be greater than 0.5, you want your z value to be positive. So that means your decision boundary is given by z equals 0. And remember, this z equals 0 is the case only when your threshold is 0.5. If your threshold is valid. So let's say you have a logistic regression model defined as f of x equals g of w naught x naught plus w1 x plus b. And then let's say you have trained the model that is, you've performed gradient descent and all that stuff, and then you have found that your weights w0, w1 are 1, and your bias is -3. And this simplifies the model as f of x equals g of x0 plus x1 minus 3, where your x0 and x1 are your features. Now, your decision boundary is given simply by equating the expression inside the sigmoid function to 0. That is, x0 plus x1 minus 3 equals 0, which is a line. As you can see in the plot, the line separates the two classes correctly. It's not limited that like we don't have any limitations that the decision boundary can only be a linear function or the linear curve. It can also be a non-linear. That is, it can have x squared terms or x cubed terms, or it can be of any shape. So if you look at the example at the right, where your logistic regression model after training, uh, is equals g of x1 squared plus x1 squared minus 1. Then the decision boundary is given by x1 squared plus x1 squared minus 1 equals 0, which is this circle, which pretty much solves the classification. That is, it properly classifies both the data, both the classes. All right. We'll have a short quiz to check our understanding till now. I'll share the QR code in a minute. I guess you can see the QR code. You can scan this QR code and join the quiz. We'll activate the quiz in 2 minutes. In a minute. Yeah. We'll start the quiz in a minute. So, what is an example of a classification task? Simple question. Okay. Yeah, it's correct. Let's go to the next question. So what type of regression is commonly used when your dependent variable X is categorical? Okay. Yeah, that's correct. So which function is used to model the relationship between dependent variable and independent variables in a logistic regression? Okay, yeah, that's correct. So in a logistic regression model, what is the purpose of the logistic function? The logistic function is nothing but your sigmoid. Oh yeah, that's correct. Okay. So most of you are right. You see if there's any doubts in your Slido, or you can also raise your hand and give you my answers. Okay, I guess
Could
there's
I
no
ask?
doubts.
Could I ask
Oh
a
yeah,
doubt?
yeah, sure. Sure.
The first question, are like both options, the cancer option and the medication option, like why are they different? Don't both of them serve the same purpose? Like you're both of them you're trying to classify. I would assume both of them should come into the same like prediction model, right?
So no, like, we're just trying to classify uh the the tumor rate. So
Yeah, but you're also
you
trying to
just
classify the patients in the first one. Like you're trying to classify the dosage that's going to be given to the patients in the first option, right? So if why is
yeah, but
the
then
model not?
you actually yeah, sure, yeah, you are right. But then what we do is we try to tell the amount of dosage. That is, you give a certain value to it, like let's say in some kind of grams, this much grams of uh, medicine should be given to that person or something.
Mm.
It's in terms of some number, not a class like okay, this guy is ill or this guy is not ill.
Okay, fine. So what will be the
But
better model for predicting if the dosage has to be given to a patient then?
yeah, so that is the you have to use your linear regression or polynomial regression in that case. First, you
Okay.
check if there's a linear relationship between your your criteria, like and then if it's a linear relationship, you will use a linear regression. If it's a non-linear relationship, you will use a polynomial.
Okay, yeah. Thank you.
Fine. Yeah. Okay. I guess there are no doubts. We'll move back to the slides. Oh, okay. So what is the main difference between linear and logistic regression? Uh, so so yeah, in linear regression, you try to predict a number. You predict to find. You try to predict a number. Like let's say for cricket 80 match, you will try to predict the score a cricket team has got at the end of a power play. That is your linear regression model. In terms of classification, you try to predict whether a team has will win the tournament or not, something like that. So the last question in this is the last question. So the last question was was what is the purpose of logistic function? So your logistic function is nothing but your sigmoid function. So in logistic regression, what we do is we want the output to be some probability between zero. So what we do is we take the output of a linear, which is some number between minus infinity to infinity. If you feed that into the sigmoid function, you get that to be between 0 to 1, which is your probability. So to find the probability of an event occurring is the purpose of sigmoid function. I think that should be all right. Fine. We'll continue with the slides. Okay. So coming to the cost function. So for any machine learning model, the most important thing is the cost function, because that is the thing that we want to minimize, right? And then you find the optimal value for your weights and biases, and then finally make your prediction. So if you recall, in the linear regression model that we saw earlier in the session, we used the mean square error cost function, which is given by C of omega w comma b equals the average of the summation of all the square of errors. So basically, your f of x is your prediction made by the model, and the y is your ground truth value or the target values you want to achieve. You just find the error between them by finding the difference between them, and you square it. Then you sum it over all the features of the problem, and you take the average. So that is your squared error cost function used in linear regression, where your f of x is given by wx plus p. In the case of logistic regression, your f of x, that is your prediction that is you're going to make, is given by sigmoid of wx plus p. Right? We'll just plot the graph for the cost function. That is, we'll plot the graph of j for both the cases, that is linear regression and logistic regression. So for plotting the cost function, like for the plotting the squared error cost function, for the case of linear regression, what we'll do is we'll use the same formula, that is you sum all the error square of the error terms to a cost table, and then you finally divide it by the total number of 2 times your total number of features. Your y prediction is given by mx plus p, which is nothing but similar as wx plus p in the case of linear regression. Similarly, for logistic regression, your y prediction will be 1 by 1 plus e power minus z, where z is nothing but wx plus p. Okay. And you similarly, you add the loss, the square of the error for every features, and finally you find the average of them by dividing it by 2 times your total number of features. We'll plot the two graphs to j graphs and see. If you plot it using matplotlib, you get to see that your cost function in the case of linear regression is some kind of a bowl-shaped graph, or you can call it a convex graph. The same when it comes to logistic regression. The graph does look pretty. It looks very interesting, but it's a non-convex graph. That is, you have a lot. As you can see here, the graph is not smooth. It goes down. There are a lot of valleys. That is, you have a lot of local minimas before you try to reach the global minimum, which is right over here. So what's the problem? Why do we? What is the problem in having a non-convex cost function plot, and what is your benefit of having a convex cost function plot? Let's look at that. So as you saw, the square error cost function, G of W, in the case of linear regression, your f of x is wx plus b. It's a convex graph, just like the one shown here. But in the case of the logistic regression, it's a non-convex one, which has a lot of local minimums before you reach the global minimum. So what happens is that, so what's the problem? When you run the gradient descent algorithm, which we saw earlier in the session, we'll be stuck in a local minimum before we reach a global minimum. Let's take the case of the convex one. Let's say you start here. You take small steps according to your learning rate value. You go slowly and then you reach the global minimum without any hazard. But let's say you do the same thing for the non-convex plot. You start here and then you do the gradients and you go here and here and you're stuck in the local minimum. Once you get to a local minimum, there's no possible way for you to update your weights and biases. That is, you cannot update your W and B further on because whatever you do, your gradient is going to be 0 at that point. So, so the you know, uh, so the gradient descent that we do, which is given by this formula or this algorithm, where Wj equals Wj minus alpha times the partial derivative of j. If you reach your local minimum, there your partial derivative will be 0, and whatever you do from there on, your weights and biases won't update. So that's why what we need to do is that we need to come up with some other cost function whose plot for f of x equals sigma of wx plus b is a convex one, just like the one we have seen here on the left, so that your gradient descent algorithm doesn't get stuck in a local minimum and it smoothly reaches the global minimum. We need to reach the global minimum because so that you can reduce your cost function to the maximum so that your accuracy of your predictions are increased. So what we do is we have the logistic loss function or the binary loss entropy loss function. So before we go on to look into what is the logistic loss function, let's clarify on two terms, which is loss and cost. So loss is nothing but the measure of the difference of a single example to its target value. So if you remember in the example which we saw earlier in the session where we tried to classify a person as obese and not obese, you take a single example where let's say you take a person weighing 60 kgs and his target value is 0, like you want to classify him as not obese. And let's say your model predicts him to be, it gives you a probability of 0.4. That means your error in this prediction is 0.4 minus 0, which is nothing but 0.4. That is your error. That or that is, you can call it as a loss of that particular example. Cost is nothing but the summation of all the losses over the entire training set. So for all the weights that you input, if you sum all the loss functions, that gives you the cost function. So let's come back to the logistic loss function. What we do here is we define it piecewise, like we define it for two particular cases. That is, when your target value is 1, you have a definition of your loss function as minus log of f of x, and when your target value is 0, you have your definition as minus log of 1 minus f of x, where f of x is the model's prediction, while y is your target value, that is the ground truth value that you want to achieve. If you plot the two functions, you get to see that it's a really smooth decreasing plot, as you can see in the two graphs below. If you look into it, why did we choose something like minus log of f of x? So let's take the case of y equal to 1. So in this case, you want your model to predict the class as 1, right? Let's say your model is really highly accurate and you have trained it very well, and your f of x turns out to be 1, that is, you predicted 1. You plug in f of x equals 1, you get the loss function as 0. Or that is what we want, right? We want a loss function to be 0 in the case where your model predicts the target value as 1 correctly, exactly. So that's why we have the minus log of f of x. And let's say your model is very bad in accuracy and then it predicts some value of 0.2 in place of predicting as 1. In that case, minus log of 0.2 would be some kind of a very high value, which indicates that your loss is too high, that is, your prediction is too bad. Similarly, you have your loss function defined for the class y equal to 0, which is given by minus y, minus log of 1 minus f of x. Putting them together in one graph, it looks like this, which is convex right now. And now you can go on to do the gradient descent algorithm and find the optimal values of your weights and biases. So the gradient descent algorithm for the logistic regression is the same as what we did in linear regression. You do the same steps where you update your weights and biases by the formula Wj equals Wj minus alpha times your partial derivative of the cost function, where alpha is your learning rate and j is your cost function. Just one small change here. Your cost function is given by the minus 1 by m summation of y times log of f of x plus 1 minus y log of 1 minus f of x. If you look closely, there is one similarity between the gradient descent algorithm for linear regression and logistic regression. It is that when you take the partial derivative of the cost function, it turns out it's the same expression that we get for both of them. It's just an observation. You can have it. So after performing the gradient descent, you get to find the optimal values for your weights and biases, which you can use it to predict the get the more highly accurate predictions. So let's see into the code implementation of logistic regression, both from scratch and using the scalar library. Okay. So for implementing logistic regression from scratch, we'll take one small example. That is, we'll take one problem where we try to classify a patient or a person, or we'll try to predict whether that person will have a heart disease after 10 years. So we'll import all the necessary libraries. We'll download the data and upload it in the using the pd.readcsv method into the df. df.head prints the first 5 records of the dataset. So this is your dataset. As you can see, you have many features: male, age, education, current smoker, cigarettes per day, and so on. And in the last column, if you look at it, that is your target values or the labels. So this tells you whether that person will have an heart disease after 10 years. So 0 means he doesn't have, 1 means he will have. So this is what we want to predict, okay, given these, using these features. To look closely into this data set, there's all the values are in some different scales. So if you look at the values in the male column, it's all either 1 or 0, indicating male or female. But if you look at the age column, it has values ranging, it's somewhere, in two digits, like 39, 46, 48, 61, and so on. And if you look at the total cholesterol column, you get to see that the values are in some 3 digits above 100 and 200s, 195, 250, 225, and so. So, is there a problem with this? Yes. If you train your model just like that, like without doing any pre-processing or of the values, that you don't bring all of the values to a same scale, what will happen is that the model will pick bias. So what it means is that it will only give priority in minimizing the cost function with respect to features which have higher values in magnitude. So let's say in this case, so the model will try to predict the cost function with respect to the total cholesterol feature. That is, it will try to optimize the weights of the total cholesterol column, and it won't give much priority to the to this column, male or age. This is because a smaller value would actually contribute less to the cost function, and so the model will think there's no use in changing the, or making a change, optimizing the smaller values because it makes very less of a change in the cost function. So what it will do is it will prioritize and optimizing your columns with the higher values in magnitude. So what we need to do is first we need to bring all of them in the same scale. In this case, we can bring them into 0 to 1. Like we can bring all the values between 0 to 1. This can be achieved using the min-max scalar function, which is available in your sklearn pre-processing library. You can simply call, you can fit the min-max scalar that will actually apply this formula. That is, it subtracts each of your values uh, by the subtracts each of the value with the minimum value of that column and divide it by the difference of your maximum and minimum values of that column. So this way, this brings all the values in the dataset between 0 to 1. Okay. And there's also one more important step we have to do with the dataset before we move on to applying any linear regression or logistic regression, which is that we have to handle with null values. So let's say you have a Google form. There would be some some blank, some what to say, some choices which are optional. So some people who take the survey, they won't need they. It's not necessary for them to fill that. So when you get your final data set or from your survey, you'll get to find that there could be some missing values in the data set, which are nothing but null values. If you go on to fit a linear regression or a logistic regression with that data set, you will you will see that your model will predict null values because of those missing data. So that's why first we need to clean the data by removing all the null functions. So there are three ways to handle the null values. That is, you can either drop the record itself. Let's say, let's say in this, in this column, there's just one null value. That is, it's fine, right? It's fine losing just one data point. But if there are many null values, it's not good to drop all of them because that would result in a very less data. So what you do is first is find the number of null values in each column using the df.isNull. So df.isNull checks if there is any null value, and then dot sum will put out the total number of null values in that column. If you run that, you will check out that in your education column itself, you have 105 missing values, and in your glucose column, you have 388 missing values. So, and if you look at the heart rate column, you just have one missing value. So it's good if you just drop that record. That's fine. But in this case, since you have a lot of your data missing, it's better to fill those values with 0. You can fill with the average value of that column if you think that that value is really necessary or important in making your prediction, or if you think that it's fine if you don't give any priority, but you just want that the rest of the values to be there, you can fill them with your 0 using the fill.na value. Okay. And also, if you look at the data set, this education column has nothing to do with the problem. Like your education doesn't really affect whether a person will have a heart disease in 10 years. Right? And also, if you see the values in the education column, it's 1, 2, 3, 4, and then it doesn't make any sense. So it's good if you just drop that column off. We drop it so that it doesn't affect your what to say, affect the predictions of the model. The next step before we you know uh, apply any regression model is to split the training data set into train, validation, and test data. So what is that? So normally we get a data set like this one above. What you need to do is you need to set some percentage. Like so your train data set. The general thumb rule is to go with 60% for training data, 20% for validation data, and the remaining 20% for test data. So what are these? So train data set is used to train the model. That is, you show the features, and then you show the corresponding ground truth value, that is 1 or 0, and then from that your model will learn and train itself. So validation data is not used to train the model, but it's used to test the model. That is, after the model is trained, you show the validation data. That is, you just show your features, and then the model will make an output. You can check the output and the ground truth values that you have, and you can compare and find the accuracy of the model. So finally, we have the test data set, which is your final data set, which on which we expect our model to make predictions. The difference between validation and test data set is that in validation data set, we know the ground truth values, they are given to us. In test data set, we don't know them, we're just going to make such predictions. Okay. In this particular example, we just split the data set into training and validation data set. We'll set aside 90% for training and 10% for validation. We are doing this because we are having very less amount of data. So we'll have 90% for training and 10% for validation. The splitting of the data can be done using the train test split method in your sklearn library. That splits the test function, like it's just the test size as 0.1, which means that 10% for validation and 90% for training. We transpose and we reshape so that it's compatible for it to be passed into the model in the sklearn library. We print the shape of the X train and Y train and check if they're equal, because if it doesn't match us, we may get errors. So you can see that there's 3814, 3814, it's fine, it's good to go. One last time, we'll just print the data set or the pre-processed data set and check if everything is right. As you can see here, all the values in the data column are between 0 to 1. Now we go on to define our model. We'll define sigmoid as nothing but it gives the sigmoid of a given value, 1 by 1 plus e power minus x. Then for defining the model, what we do is we first initialize the weights to be some random values, and your bias to be 0. We also have a cost list, which will be appending the cost after each iteration. So what we do is, for each iteration, we'll find the prediction, which is given by sigmoid of z, and then you find the cost function, which is given over here, and then you perform the gradient descent, which is simultaneously updating your w and b, and then finally you append the cost list to the cost function, cost you find after every iteration. We also have a accuracy function, which will give you the accuracy of the prediction that the model has made. If you look closely, we have also set the the thresholding as 0.5. We'll look into it how your model's predictions accuracy will change if you differ the thresholding values in a minute. So for this particular case, for the threshold of 0.5 and the number of iteration to be 100,000 and a learning rate of 0.001, you see that your cost function is decreasing very well, and your accuracy turns out to be 84%, which means that your model is predicting with an accuracy of 84% on your validation data. That's good. Now let's see what happens if I change the threshold to be 0.4, let's say. We'll run the model again. So we're printing the cost after every 10,000 iterations. Okay. So this time, if you see, your model's prediction accuracy is gone up by some amount. So your prediction is gone, or it's almost like the same 85%. Right? Now let's see what happens if your threshold is from 0.55. Okay, let's run the model again. All right. So if you see here, your accuracy has gone down, means it has become 84.91. So by adjusting the threshold, which is a hyperparameter, that is you can adjust it such that your predictions increase. I mean the accuracy of the predictions increase. So in this case, probably 0.4 is your good threshold value. We'll do the same implementation using scikit-learn. So we have done this earlier, which is nothing but you just import your logistic regression model from your sklearn library, and then you do the same train test split on the data, and then you simply feed in the explain and worry to the log, like which is your model's instance that you have created. Then you make the predictions using the dot predict method. Finally, you predict the accuracy using the accuracy dot underscore score method, which turns out to be 85.38. So if you observe, it means that you get your accuracy for your scikit-learn implementation to be higher than implementation using Scratch. So this is because your sklearn library uses optimizers and regularizations, which we'll learn in upcoming sessions in the summer school. So for now, you can understand that it's more because it uses optimizers and regularizations and all those. We'll go back to the slides. Okay. So now that we are seeing classification for, we are seeing binary classification where you need to just classify a given sample into two classes, that's a positive class and a negative class. In that case, a sigmoid function really serves the purpose. So what happens if you have multi-class? Let's say you want to, you want to input an image of an animal, and you want to predict whether it will belong to the class dog, cat, or horse, or cheetah. In that case, your sigmoid function doesn't work. Why? Because your sigmoid function is simply going to make your input between 0 to 1, but it doesn't make your probability distribution with respect to the rest of the classes. So it just makes your breaks down the value to 0 to 1 only for two classes. So that's why we need another function that can do the job. That is your softmax function. Whose formula is given by e power x by summation of e power, the e power x value for each of the features. So as the example given over here, let's say you input a dog, image of a dog, and then you get your raw predictions as 3.2, 1.3, 0.2, and 0.8. And if you apply the softmax function to it, you can see that it's converted to probabilities, and then if you add all of them, you get one, and that's what we need. So the thresholding for multi-class classification would be such that the class with the higher probability is your final prediction. That is, in this case, your class dog has a probability prediction of 0.775. So we make a prediction that this is a dog, and which is correct in this case. All right. So Are there any limitations of logistic regression? Yes. What logistic regression does is that it will generally assume a linearity between the input features. That is, like it will always try to express the given problem in terms of like W1 x1 plus W2 x2 and so on up to Wn x1 xn plus b. But in real life, that's not always the case. Like, let's say you have a YouTube ad, and then you want to find whether a customer who watches that ad will purchase that product after given its features like the age of the customer and the income, right? The relation between age and income may not be a linear one. That is, it can have some powers of x, like x square or x cube or something. In that case, logistic regression does. But if you recall moments back, we've seen that logistic regression can also have nonlinear boundaries, like over here, like a circular boundary over here. In this case, your input to the sigma function is x square plus x square, which is what the case nonlinear relationship between your features. So what we do here is that we do something called feature engineering. That is, let's say you want to predict the price of a house. You're given its features like length, breadth, and height. From the given features, you can engineer two another features, which is nothing but the area of the house by simply multiplying your length and breadth. That would result in a feature having the power of 2, that is x squared. Similarly, if you multiply length, breadth, and height, you can get the volume of the house, which will give another feature of x cube. Right? In that case, your decision boundaries can be non-linear. But in general, your logistic regression model assumes a linearity between them. To solve the problem of non-linearity, there's another model called SVMs, support vector machines, which will be covered in the next session. So please do check that also, which deals with non-linear patterns in data, which is what we find in real life. So yeah, so that is your logistic regression. You have learned the most powerful supervised learning for classification problems. Let's end the session with a small quiz. I'll share the QR code. Okay. You can join the quiz by scanning the uh, QR code. I'll start the quiz in another 2 minutes. So yeah, for gradient descent algorithm, having a convex graph is often desirable. So why is a non-convex graph not desirable? Yeah, that's correct. Next question. For a target value of y equals 0, what is the expression for your logistic loss function? Oh yeah, that's correct. Yeah, but most of you went with the option A, but option B is correct. Like the question is asking only for the case where your target value is y equal to 0. The last question. for the day. So in predicting the presence of cataracts using logistic regression, what could be a practical threshold? Yeah. All right. But the answer is 0.3. So an ideal thresholding would be 0.5. Okay. So if you take the case of ideality, like you say, you want to predict you want more positive cases and more negative cases, that would be 0.5. But it's always better to have a threshold of 0.3 in this particular case of predicting the presence of cataracts, because it's if you have a lower threshold, that would mean that your model is going to predict more positives, which are going to be false. That's fine. But in the case of some medical issue, it's always better that you don't take any risk of leaving out any possible positive cases. So setting the threshold to be less, and then having a medical practitioner who can diagnose the results further would be preferred. So that's why for this case, having a threshold of 0.3 would serve the purpose. And yeah, so that's it. Yeah, yeah. So yeah, so that's it for the day. We'll see if there's any doubts. We'll check the doubts.
Yeah. Right.
Okay.
Listen, those of you who want to leave can leave, but if you want a little more insight on task one, stay back for a bit. I will present my screen and show how exactly to go about task one. Continue, Pratosh. Deal with the doubts.
Okay. All right. So there's a question on is min-max scaler used for feature scaling? Can we use standard scaler in that case? So yeah, so in the example that we did in this session, we used min-max scaler. We can also use standard scaler also. But for this particular term that I took today, I used the min-max scaler because that was giving me better output, better predictions. So you can use different methods of scaling, like min-max scaler or standard scaler. Okay. So may I know what single imputer is? Okay, I couldn't get that question. Alright, then I think there aren't any doubts left. So if there's any doubt, you can raise hand and you can unmute and speak. So I guess we can close the session if there aren't any more doubts.
Yeah. Also, the person, whoever is asking that question, may I know what simple imputer is? Simple imputer is basically one of the functions that is available in sklearn in order to handle the missing values. So I guess Pratosh has already mentioned in his implementation, what he did was he replaced all the null entries with zeros. So there are also other strategies, like you can use mean, or you can use some other values as well, or you can even completely drop the rows. So sklearn provides you with this functionality of using either of these strategies by using sklearn.simpleimpute. I guess that should clear that out.
Pratosh, stop presenting. I'll present my screen and give some inputs on task one.
Fine.
For those of you who have doubts on task one, this is what you're supposed to do. One second. If you go to the repository, GitHub repository, for anything and everything, all the doubts you have to go to the repository. Once you go there, you will see a task one folder. Under here, you will see the description of what is going to happen. There is a data set If you click here, you can see the data set. It is pretty huge. From this given data set, there are multiple columns. Each column, there is a description given. Read through the instructions. There is also a submission form here. Read through the instructions. See what you're supposed to do. Essentially, what you're supposed to do is you're supposed to go through the data set from whatever you can observe, like try to plot some of them, try to bar graph some of them. You have to decide on what you have to do and see how it performs, how the data set looks. In order to do this, what you're supposed to do is when you go to the data set, you will see a download folder. Click on the download button. You will basically download the file. You will download the dataset file. Once you have done this, create a new collab notebook. Wherever you are working on, you will be able to create a new collab notebook. Once you do that, come to the folder button. There will be a folder button here. Click on this and you will see a file upload option. Once you click on the file upload option, you will be able to upload the file. Okay, got this? Now, once you have done this, as we taught in this session, you will be able to read the data now. Let's say I have data is equal to pd.read CSV. And you have to copy the path. To copy the path, you can simply click on the three buttons and say copy path. It will get copied and you paste it here. And you run this cell. Once you run this cell, the entire data in the CSV file will be stored in the variable data. Now, if I call data, it will output all the rows you have and all the columns you have. You can see all the columns, all the rows. Now you can plot or you can do whatever you want with it. Let's say if I want to plot tenure versus serial number, I can simply say plt.plot data s dot, I think, yes, s dot capital M-O, comma, data and tenure. You can see the plot. The plotting is very bad because obviously the legend is the plotting points are very different. You might have to use white ticks over here so that the ticks are properly aligned. And pretty much you can't infer much from this data. So there's no point in plotting these two. You have to go through each one of those columns and you might have to plot them. That is what we are trying to see. You can even plot it with age. Let's plot it with age. Maybe that might be a little more sensible. That is also not sensible either. Let's say if I want to find out the mean of the age, np.mean data age. This is the mean age in the data set. You can simply say this is the mean age, and you can maybe write down a markdown saying the mean age is 28.54. This is what we'll be expecting. This is what we want from task 1. I hope all your doubts are clear now. Got it? Any more doubts about task 1? Ask now or on the WhatsApp group also it works. That's all from the session. Hope you enjoyed it. Next session will be on, I'll show on the GitHub repository itself, will be KNN's, SVM's, naive-based classifiers. They are a little more complicated than linear, logistic, and polynomial regression. They are one step complicated. That's all from the sessions. Have a good night, friends. Bye-bye.